let me mention a few key aspects of what we want to do in this class in the context of very simple systems. So essentially, I want to distinguish or point out one of the key differences between linear and nonlinear systems. And let me just do that in an extremely simple context where imagine we have a differential equation dx by dt is equal to f of x and mu. And mu is a control parameter that we can change. And so in the linear case, if I plot f of x and mu, it may look like that. And let's say I'm actually right now mostly interested in just in fixed points, in critical points, stationary points, whatever you want to call them. So in this case, I'd be interested in this point here. And if I have a linear system, meaning if this function is here just a straight line, the only thing that can happen when I change a parameter is, well, the straight line could look like this, could look like this. And that means that this fixed point, it moves to the right. That's it. I mean, you can't really, there's nothing else that can happen. The only thing that can happen is that eventually it disappears at infinity, maybe. But that's it. There's always a fixed point. There's always one fixed point. In contrast, if you have a nonlinear system, so say we have a function that looks like this. So then I have a fixed point. You see that right away. I have a fixed point here. If I now change the parameters, I don't have to do any fancy changes. I could just imagine, well, maybe the curve shifts downward. And then suddenly I have this fixed point plus two more fixed points. So the number of fixed points has changed. So really the system has changed qualitatively. It's not, now it really depends on where you start to know which final state you will end up in. And so that's a minimal version of what I said earlier for these experimental systems, that you have all these transitions between different states and they're qualitatively different. So what are we aiming for? Well, because there's these qualitative changes, the first thing we want to actually understand are just the qualitative nature of things. So we're not so much interested in the value of this fixed point or stuff like that, but rather we just want to know how many fixed points are there and what happens when some disappear. How can they disappear? How can they arise? And we want to have an overview of the possible solutions for that system. And we get that, qualitatively. A lot of that is essentially visualization. We understand how the phase space looks. We just have a phase line, higher dimension, we have phase space. We want to know how the phase space looks, what kind of solutions are there, and what kind of transients would there be. And these are things one can do analytically, or to a large extent, one can do analytically. And one tool that is very powerful in this context, in terms of understanding the transitions, is becomes apparent when you look at the case where the transition occurs. So this is when I have this intermediate case where these two fixed points just come together. And when I change the parameter just a little bit more, which is not hard to do because the plot is almost full, but you see now there's no fixed point. But you notice the following. If I look at the dynamics in this case, the dynamics are given by f, right? And when this fixed point disappears, because this minimum detaches from the x-axis, at that point f is very small, which means that dx by dt is very small. So a characteristic feature of many of these transitions, of these qualitative transitions, is that some kind of dynamics become very slow. So let me note that down because that's a really important aspect. It's not always the case, but often the dynamics become slow. Slow. And this means that you have multiple timescales. You have a timescale separation, and that allows you to simplify systems substantially. for instance, these fluid flow systems in the vicinity of such a bifurcation, even though you're starting with a PDE in 3 dimensions, you actually describe the transition itself just with a single ODE. And that's one of the powerful things that are going on here. And its key aspect is that you have time scale separation. You have slow dynamics. Let me just mention in passing, slow dynamics here arises from the bifurcation. It doesn't have to arise from the bifurcation. There are other cases which we hopefully get to also, depending on how much time we have. But slow dynamics arises from the fact that some quantity is conserved, meaning, so that's, well, let me just leave it at that. The quantity is conserved, or because you have a broken continuous symmetry, and that also leads to slow dynamics, or you have objects that are interacting with each other, but weakly so, because they're maybe far apart from each other, and that also leads to slow dynamics and separation of time scales, so you can reduce PDEs or many ODEs down to single ODEs or just a couple of ODEs. So that's one of the key elements of what we're going to do and spend quite some time on it. But it's going to be fun.